Good afternoon, students. We will continue our discussion on MOS device structure and the current equation. So, last day we have seen the device structure of MOSFET including both NMOS as well as PMOS. So, we have also discussed how the channel is inverted and what is the threshold voltage of the MOSFET, right. So, if we provide a positive gate voltage, then there is a depletion layer is formed beneath the channel, right. So, this is the Q depletion, okay. The total charge of the depletion region that we can formulate by this equation, that is square root of twice Q N, Na is the accepted ion doping and epsilon silicon and phi. So, this phi is Fermi potential and this is our total charge, and this depends on the Fermi potential as well as the backgate voltage. For this moment, let us consider that source and bulk is shorted. So, VSB is equal to 0. Okay. So, if this is the condition, then initially we have discussed last day also that when there is a depletion region is formed, then this region formed like a capacitor, behave like a capacitor, right. So, we have two capacitor in series, one is oxide capacitance, that is due to the SiO2 between the gate and channel, and another is the depletion region that is formed between the beneath the channel and between the substrate connections. Okay. And if this voltage is overcome, threshold voltage Vt is defined as there is a Vt 0, Vt 0 is the initially if it is VSB is 0, then what is your threshold voltage. Okay. So, Vt 0 plus this gamma, this is known as the backgate coefficient or body coefficient, and the expression is like it depends on the VSB and the twice phi f. Okay. So, we will discuss about this and what is this backgate effect, what is this body effect coefficient and how we can model this, that we will discuss during the second order nonlinear effects. So, that we discussed in our last class, that how the steps are in pictorial form, right. So, this is the first step when you are providing a positive gate voltage, then a depletion region is formed, and if you go further above threshold voltage, then a inversion layer is formed. Now, if we want to calculate that how much current is flowing or how to calculate the current, then let us consider that a unit chunk of electron is as if flowing. Okay. So, if we up to this, when a channel is inversion is happening, because my gate voltage is above threshold voltage, right, then the this P substrate is inverted. By default the majority carriers of this P substrate is holes, but when the gate voltage is above threshold voltage, then what happens, some electrons are coming, right, from the adjacent source and drain region. And now, if we provide a positive voltage at this drain terminal, then electron will move, right, they will feel a lateral field also, right. So, due to this lateral field, they will be attracted towards this direction, is not it. So, let us consider that a unit chunk of electron is moving with a velocity v, right, and let us consider that its charge density, that is charge density, that is charge per unit length. Okay. So, this QD we are defining like its unit should be coulomb per centimeter. Okay. So, this QD is not total charge, this is charge per unit length, clear. So, now if we want to get the current, you know what is current? Current is equal to Q per Q by T, right. So, you know that current is Q by T. So, you see this is Q by D. So, if we multiply this with D by T, then I will get current in ampere, right. So, in other way, if we multiply this charge density or QD with the velocity, what I will get? Current. Clear? So, how we are progressing? We are considering charge density. What is this charge density? It is charge per length. So, what should be our total current? Current should be QD into V, where V is the velocity at which the electron, unit electron area that we have considered is moving. Clear? So, what we have considered? We have considered a unit chunk of electron, and because of the lateral field that is we are providing at the drain terminal, it is feeling a attraction towards this direction and it is moving, right, and it is moving at a velocity v, say v meter per second, right. So, if we multiply our QD, we will get the current. Now, we all know that when the channel is inverted above VTH, right. So, effective get to source voltage, it should be above overdrive voltage VGS minus VTH, right. There is no doubt about it, because after it is crossing VTH, then only channel is inverted. So, this phenomenon will be happening VGS minus VTH. Now, you consider this is a source, this is our channel and this is our drain, right, and this is a positive voltage, and this is our oxide region, this is our gate region. Now, see, we have applied a positive voltage here, right, and the if suppose there is no voltage, suppose this node is ground. So, whatever the VGS we will be applying, that will be effective throughout the channel. Clear? Suppose there is no drain voltage. So, whatever the vertical field VGS is providing, that will be effective to make the channel field, right. Now, what we have done? We have provided another potential here, that is Vd. So, this Vd will be fighting with this field, right. So, what is happening? Suppose at a potential at a distance x, due to this Vd, a voltage of Vx is appearing at this point. So, effective voltage will be, right, the effective vertical field, that will be VGS minus VTH minus Vx at position x, that Vx is subtracting because of this drain potential. You all know that, because suppose there was no drain potential, my channel will be uniform. Now, suppose I have start to increase my Vd, so this will fight with this field, right, and this channel will become tapered, right. You know this. So, if we further increase our Vd, what will happen? This channel will ends before it reach the drain junction. Why? Because the effective voltage is now what? Suppose your Vd is equal to just overdrive voltage. So, effective voltage at this point is V of V minus V of x is equal to V of V minus V of V is equal to 0, right. So, no vertical field at this moment. So, channel is just stopped there. That will come when this is known as what? pinch off and channel length modulation, right. So, we will come to this. So, to have this effect of VDS, what we are modeling, that this is the effective voltage that will be the driving force behind this movement of this QD, okay, or the electron chunk, right. So, if we do not have any drain potential, then this is VGS minus VTH, this is our effective voltage, and that I should multiply with what is Q? Q is equal to CV, right. So, what is your total C? Your effective capacitance is COX. What is the unit of COX? C oxide, it is femtofarad per micrometer square, right. So, it is say femtofarad per micrometer square. That means, if you multiply it with your total area, you will get the total cap. But what is this QD? QD is charge per length. So, we will not multiply with W into L, we will only multiply with width, because QD is coulomb per meter. So, we will not multiply with micrometer square, we will be only multiplying with only width. Okay. So, what we are doing? We are just multiplying COX with W, because QD is charge per length. Okay. So, we will not multiply with length, we have considered that way. Okay. So, that we get this current I is equal to QD into V, that is why we have modeled it that way, or you can do it with total charge also, ultimately that will be coming to the same point. So, that into V, and that V is your effective voltage. So, if we have a drain potential, so what is my effective potential at position X? That would be VGS minus VTH minus Vx, clear. So, let us come to our discussion. So, that is the effective potential. Okay. So, total charge density QD is equal to C into V, right. So, our QD is equal to COX into W into VGS minus VTH minus V at position X. That V at position X is coming due to the portion of the drain potential, okay, effect of the drain potential. Okay. So, this is our total QD. Now, what is I? I is equal to this Q into V, okay. And what is our V? This velocity is mu n into field, okay. So, now we all know that current is equal to QD into V, where V stands for velocity of the unit chunk of this electron, and that is we can define as mobility of the electron, because at this we are talking about NMOS and electron only. So, mobility of the electron, that is mu n into electric field, okay. So, electric field is equal to mu n, that is dV dx, okay. Electric field is potential divided by distance, right, potential per days. So, this is potential, okay. This is electric field. Okay. So, if we for this moment if we neglect the minus sign, so it will be COX W VGS minus VTH minus Vx into mu n dV dx, right. So, this if we model this for total channel. So, if we consider that it is starting from channel at position 0 to at position L, L is our total channel length, right. So, if we can integrate this current over a total distance of L, right, if we can integrate this over a distance of L, then we will get the total current, okay, of the MOSFET. So, what we will do? We will integrate this I from x is equal to, x is our position, x is equal to 0 to L, and the voltage is varying from V is equal to 0 to V is equal to VDS, and we will get the total current expression, right. So, x is equal to 0 to x is equal to L ID into dx is equal to integration V is equal to 0 to V is equal to VDS full scale voltage COX W mu n VGS minus VTH minus V of x into dV. Okay. So, what you get if you integrate this? In this side you will get ID by L, ID into L, right. This side COX W mu n VGS minus VTH into V minus half V square, right. VGS minus VTH, say this is VDS, so it should be VDS minus half VDS square, agree? Okay. So, what is your I? I is equal to L will come to this side. So, I is equal to COX W by L mu n VGS minus VTH into VDS minus half VDS whole square. So, let us make it ID is equal to W by L. So, this is your equation 1, or this is the total current expression, right. From this current expression you will get all the current, right. So, this is your current expression, okay, and that is how you derive it. Now, that is the plot you will get if you plot this. Now, few important points we can discuss from this. Say VDS is very small, VDS is very close to 0. Okay. So, what you can do with half VDS square? You can neglect. Okay. So, if you consider that VDS is very small and neglect this, your expression becomes mu n COX W by L VGS minus VTH into VDS, is not it? So, what is that? Deep triode region. So, our expression is ID is equal to mu n COX W by L VGS minus VTH into VDS minus half VDS square. So, one expression we have seen that if VDS is much less than VGS minus VTH, so this square term we can neglect. This is known as the deep linear region, right. So, the MOSFET is in deep triode, and your current expression becomes mu n COX W by L VGS minus VTH into VDS. So, if you plot this, you just see that this is nothing but y is equal to mx, right. This total expression, if you consider that for a particular VGS, for a particular VTH, this expression is constant, and this is just like a this is just like a Ohm's expressions, right, Ohmic law. Clear? So, now we have a condition that VDS greater than VOV. If VDS is greater than VOV, this region is known as saturation. Another is VDS is less than VGS minus VTH, that is your linear. So, now if you plot, so this is the demarcation, right. So, this is your VDS, this is your ID. Now, this is your MOSFET. Here you are applying one variable voltage, that is your VGS, and here you are applying one another variable voltage, that is your VDS. So, you are getting a variable current ID. So, what is the meaning? How many variable are there? One variable is VDS, another variable is VGS. So, if you have different VGS, you will get different set of equations for ID, right. So, this is known as the graphical plot. From this graphical plot also you can calculate the same thing. Now, suppose let us consider that VDS is just equal to VGS minus VTH, then what happens? Half VDS square and this term, they becomes, your ID becomes half mu n COX W by L VGS minus VTH whole square, right. This is at, so this is the expression for which current? Saturation current. In this saturation current, can you see any term for VDS? No term for VDS, right. So, what is the meaning? That even if my VDS is changing, my current should not change, because in my equation there is no dependency of VDS, right. But in reality, what you see? This current do depends on VDS, right, is not it? So, if you extend this, it will cut at which point? You all know that, that is called early voltage, right. Okay. So, if this is the reality, then I need to change my equation. How we can change the equation? So that it will depend on VDS also, 1 plus lambda VDS. So, what is this known as? Channel length modulation effect, right. So, what we will do, that this same expression ID should be ID sat into 1 plus lambda VDS. So, now my current, if VDS is increased, my current will also increase. Okay. So, from the expression we can model it for all the regions. Okay. So, this is our total current equation. From this, if we put different conditions, first condition is VDS is much less than VGS minus VTH, we will get the expression for the deep triode region. Okay. That is a totally a, this is you can say that deep triode. This is our linear region, this is our saturation region. So, three distinct regions, and only a single equation you can, if you put the conditions, then you can come to the different values. Okay. So, that we already discussed. So, in this parabola, if you try to find out what is the peak, that is you put VDS is equal to VGS minus VTH, you will get this maximum current, that is known as the saturation current. And to make it dependent on the VDS, what we can do, and this is our linear deep trough region that we are talking about. In this case, it just behave like a linear resistance. Okay. And this is our expression for the linear resistance. Okay. So, in this expression, if we try to find out delta VDS by delta ID, we will get what we will get? We will get R on. Okay. So, you do not need to memorize this, just the single expression ID is equal to what, from that you can calculate what is R on. Okay. This R on is important because in all the digital circuit, if you want to calculate the delay of your logic gate, you have to calculate this R on. Okay. So, now another question that you can also answer, that why in digital circuit you go for a minimum size or minimum length transistor. So, your R on is proportional to L by W. So, you should reduce R on as low as possible, and to do that you should use the minimum length, because in digital logic your transistor is operating like a switch, and if it is a switch, it should either be turned on. If it is on, its resistance should be 0, if it is off, its resistance is high, right. In off state, cutoff is taking care of high resistance, but in on state you should model it so that its R on is low. So, as its R on is proportional to L by W, you should choose L minimum. Another advantage of choosing minimum length is your packing density is quite high. So, you can go with large number of transistors. Okay. Another thing is that with minimum L your current will be more, right, W by L. Okay. So, your driving strength will be better for a given W. Sometimes we model these mu n C x with k n dash. Okay. So, this is a technological parameter. So, mu n C x generally sometimes you will be seeing that this is replaced by k n dash, and mu n C x W by L is known as the k n. Okay. So, that is the tapering that we are talking about, that if we have a drain voltage that is higher than your overdrive voltage, then what will happen? Suppose this VDS is just equal to VGS minus VT. So, this effective field will start after VGS minus VT, and at this moment it will just equate each other, right. The effective field that is forming the inversion of the channel, that is VGS minus VTH, and this voltage is also VGS minus VTH. So, it will just end at this moment. Now, if you keep on increasing VDS even higher, so what will happen? This will keep to move towards left, right, and tapering of the channel will happen, and this is known as the pinch off, and this is the reason. So, what is happening if due to this pinch off your effective length is increasing or decreasing? Decreasing, and your current is W by L. So, now L is decreasing. So, I should also increase, and that you see in this effect. Okay. With the increase of VDS, what is happening? Your channel length is modulated, right? Channel length is decreasing, and as channel length is decreasing, from the equation you know that you will get more current. Okay. So, you are getting more current, and that if we want to model, so as if we will see that as if VDS is increasing, my I is also increasing. So, we will take a linear dependency on VDS, and that dependency is 1 plus lambda VDS. Okay. So, this slope gives you a hints of the resistance, right. If you invert this, you will get the resistance, right. This is your del I, this is your del V D. So, if you invert this, you will get the R naught. R on was the resistance at the linear region, right. Capital R on was the resistance at this region, and in this region your resistance is denoted by R naught, small r naught. So, this resistance, what is the unit? Voltage by current, right. So, this is what should be the unit of this lambda? You are multiplying this with a current and you are getting a current. So, unit of lambda is 1 by V. Okay. So, that V is cancelled, your unit remains current, because here I have a current expression, right. This is I D sat and I am multiplying this with 1 plus lambda V D S. So, unit of lambda is V inverse. Okay. So, if unit of lambda is V inverse, can you tell me what should be the R naught? V inverse. So, if we give 1 by lambda, this is 1 by V, V will go to up and we multiply it with it only I D. Clear? So, the resistance at the saturation region is 1 by lambda I. Okay. This lambda also you can 1 by lambda you can also replace with sometimes VA, early voltage, okay, VA by I, that will also give you a resistance. So, these are small things that will give you confidence about the while doing the design. Okay. So, I told you that we are having two variables, actually we are having three variables. One variable is our VGS, if we vary this our current will also vary. Another variable is VDS, that is at the horizontal line we are varying. So, if this is varying our region is changing, okay. And third variable is our ID, depending on the value of VGS and value of VDS our ID can also change. So, this plot gives us 3 set of current for 3 set of VGS, and if we vary the VDS from 0 to VDD, we will get different region of operation. Okay. So, for digital design, this is your region of operation, this is your linear and this is your cutoff. So, on and off. So, these two region you will be playing, that we will confirm it while doing the discussing the VTC of an inverter. We will cross check that the MOSFET are operating at the linear region. Okay. So, we have covered the calculation of current expressions, how to calculate the current expression considering the unit chunk of electron moving because of the drain potential, and how to calculate the I depending on QD into velocity, and then we calculate the current, and for different regions of operation we have considered how the it will behave, and we also see that if our VDS is greater than the overdrive voltage, pinch off will occur. Now, this is transconductance is another figure of merit that we often use to express the strength of the transistor. Okay. So, if you see this, that in saturation your current is a function of VGS minus VTH whole square, right. So, if you provide higher VGS, you will get higher current, if you provide lower VGS, you will get lower current. So, if we can define some parameter, that is transconductance, as del ID by del VGS. Okay. So, this will give us a hint that how this transistor can behave like a current source. If GM is higher, my transistor can give a higher current. Okay. If you multiply with VGS minus VTH, overdrive voltage. So, this GM gives us the hints about the how strong the transistor is. Okay. So, in saturation region, your expression is ID is equal to half mu n Cux W by L VGS minus VTH whole square. If you take a derivative, what you get directly? Mu n Cux W by L VGS minus VTH, is not it? Your current expression is half mu n Cux W by L VGS minus VTH whole square, that is your ID. You take a derivative del ID by del VGS, you will eventually get this. Okay. This 2 will come out, this half will get cancelled, and it is mu n Cux W by L VGS minus VTH. So, this is the expression for your GM. You do not need to memorize this, just only you remember this expression. Okay. And you can calculate this. Now, you see this expression and this expression, do you need to memorize it? This is the same thing, right. So, what we did? We just put the values of I. We have convert this expression in terms of I and just modified the terms, so that this equation and this equation are same, right. So, what is our I? I have to put one half here and I have to make it square. So, what we are lacking? We are lacking one 2 and another VGS minus VTH. So, if we multiply this with 2 mu n Cux okay, W by L and take a square root, this will eventually come to these expressions. So, same expression, but they are expressed in 3 different format. So, can you tell me that why it is necessary to have 3 expression, why they have done so, why not they only stopped after a single expression? Is there any necessity? These are all same expression, right. That expression and that expression, what we did? We just remove these square terms and twice ID we write the expression of ID and you divide it with VGS minus VTH, you will come to the same expressions. So, all 3 format, but same thing, right. So, why actually we do this? Because of this. So, you see that we are plotting GM with respect to what? What is our variable and what is a constant, that you should understand. Okay. One condition could be that my circuit design is fixed, WL is not going to change. So, if I plot GM with VGS, then we can say this is not going to change, then GM and VGS minus VTH is shows like a linear relationship, right. So, what is the meaning? You see here W by L value is constant, but is my current constant? No. Why? Because VGS is changing. If VGS is changing, my ID will also change. Now, suppose your circuit is something like this, that you are using a current source. So, now your current you are forcing to be constant, right. This case, if I draw the circuit, it is something like that. This voltage you are varying. So, if you are varying this voltage, this ID will also vary, but its W and L it is fixed. Okay. So, GM if you plot this, it will look like this. Now, say I replace this R with a constant current source. So, this constant current source is forcing that I is equal to constant. In this case also W by L is constant. Okay. This I can vary or not. Then if in this case this is the third case, that I d is constant, but V g s minus V t h is a variable, W by L you can keep a constant. So, depending on your conditions you will get same GM, you see same GM, but it will behave in 3 ways. Okay. So, do not get confused, because what is your variable? If you are varying with respect to VGS, if your VGS minus VT is increasing, GM will also increase. So, you get a this plot, right. In this case, yes, in this case you see your ID is constant, Now, if you increase your VGS minus VTH, you are dividing it with VGS minus VTH. If you are increasing VGS minus VTH, your GM will decrease. So, if you are increasing VGS minus VTH, GM is decreasing. So, do not get confused between first plot and third plot. You will be saying that here VGS minus VTH increasing, GM is increasing, but here VGS minus VTH is increasing, GM is decreasing. Conditions are different. Okay. In this case, ID is not changing, ID is constant, which is forcing the GM to be going down. In this case, ID has the freedom to go up, and as it is going up, it is pulling up the GM also. Clear? So, these three are the same expressions, but depending on what are the criteria, which one is constant, what are the third variable is doing, you will get a 3 different plot. Okay. So, this will actually give you a hints about how the your transistor is doing and how strong your transistor is. If you see this plot GM versus VDS, okay, your gate, what is your gate voltage? VB, VGS is equal to VB. So, after which point inversion happens? V overdrive voltage is equal to VB minus VTH. So, after which point your transistor enters into saturation? VDS greater than equal to overdrive voltage. So, VDS greater than VB minus VTH. The moment transistor enters in saturation, your current expression is VGS minus VTH whole square. There is no dependency of VDS. So, GM will become constant. We are considering the ideal expression. In ideal expression, the transistor enters in the saturation region. When it will enter into saturation region? When VDS is more than the overdrive voltage. What is that point? VB minus VTH. If it enters into a saturation region, your current expression is half mu n CoX W by L VGS minus VTH whole square. So, there is no dependence on VDS. So, my GM will become flat. Now, let us see the other thing, when it is in linear. I told you it in linear region your expression is, suppose say deep triode, mu n CoX W by L VGS minus VTH into VDS. So, if VDS is decreasing, my GM will also fall, right. So, in linear region, as my VDS is decreasing, GM is also falling. Okay. So, that already discussed about the one second order effect, that is channel length modulation. Now, another effect is body effect, that we already have seen the gamma coefficient, right, body effect or body bulk gate coefficients. So, what is that and how does it modify your threshold voltage. So, if you recall, initially we assume that bulk and source are shorted to ground. So, your VBS is equal to 0, right. Now, say this is a NMOS, right. This is a P substrate, right. So, in P substrate what is your majority carrier? Holes, right. Now, let us see that, let us assume that Vs is greater than Vb. Okay. It may happen, right, if we have two NMOS in series, then this source is at ground, but this source is not at ground, right. So, its bulk is at ground, its bulk is also at ground, but its source is at some higher potential from ground, right. So, let us consider that condition, that Vs is greater than Vb. Okay. So, you can say VSB is greater than 0 or VBS is less than 0, same thing, right. VSB is greater than 0 or V source is greater than V bulk or VBS is less than 0. This is okay. All are the same thing, right, same expression. Now, if my source potential is higher than bulk potential, the same thing I can express like this way, that source is ground, but bulk is at a negative potential. Okay. So, this same thing, as this will be modeled like VBS less than 0, same it is modeled here by this expression, that source is at ground, but say suppose that bulk is, you are forcefully making it to some negative potential, that you can do. Okay. So, if you connect this to a negative potential, what will happen to the holes? They will feel attracted, isn't it? So, all the holes, they will feel a downward attraction towards the substrate connections, isn't it? Okay. Clear? So, first condition, suppose you do not have the Vb less than 0, you are starting with initial condition Vb is equal to 0, V source is equal to 0. So, to invert the channel you need to provide a certain potential of Vth, right. First what will happen? First step, if you recall, I provide a positive gate voltage, it will repel the holes. So, if holes are repelled, what will remain there? Immovable negative ions, right. So, I have given a positive voltage at gate and holes are repelled, and what remains is immovable negative ions. Suppose because of this condition there are 5 immovable ions. Clear? Up to this clear? Now, on top of this what I am doing? I am making this Vb is equal to some minus potential. So, that minus potential will also do the same thing. It will also repel the holes from the channel towards the down. So, what will happen? Previously there were 5 immovable ions, now because I have given a negative potential at the bulk, another 5 immovable ions are depleted, because that negative potential will attract all the holes, right. So, as the holes are moving beneath the channel, so another layer of depletion region is formed. Up to this okay? Clear? So, in case 1, if you need to invert this, right, if you recall our VTH expression, that VTH threshold voltage depends on our total depletion charge, is not it? So, if you want to add more positive charge on this gate terminal and this is balanced, then what will happen? If we increase little bit more, then electron will come out of this junction, right. But now in this case, you see, compared to case 1, in this case 2, I have to provide more gate voltage, right, because in this case there were 5 unbalanced ions, now in this case 10 ions, right. So, I need to provide more gate voltage, right. Suppose in this case it was Vx, so in this case it should be more than Vx I need to provide. Is it okay? Because this negative potential of this bulk, what it is happening? This Q depletion is increased, that is, you agree? My depletion width is increased. If depletion width is increased, you see, my total threshold voltage, that depends on the work function difference, Fermi voltage, and the, if you have a cap, voltage is equal to V is equal to Q by C. So, if my Q is increasing, my threshold voltage should also increase. So, backgate voltage in this condition is increasing my threshold voltage, clear. So, if I have two MOS connected in series, so its source and bulk is at 0, but its source is at higher potential. So, if this is M1, if this is M2, which one will have higher threshold voltage? M2 will have higher threshold voltage, because of which effect? Body effect or backgate effect, clear. Why? Because its bulk and source is 0, but its source is at higher, it is having a VSB, that VSB will modulate the threshold voltage, clear. So, this is your body effect. Okay. So, that same thing is expressed in this equation. So, you can understand that if V source is higher than V bulk, your VTH will go up for MOSFET. Okay. This channel length modulation we already discussed, so we do not need to discuss this. And this body effect, how to model? Generally, we model GM like a this na, GM into VGS, right. Then there is a R naught, right. If you want to model the backgate effect, we will model this with another current source and we will make it GMB. Clear? So, this transconductance models our variable current source, and this backgate, due to this backgate also our threshold voltage is changing. If threshold voltage is changed, your current value will also change, because your current depends on VGS minus VTH. So, if suppose backgate voltage, threshold voltage is little bit modulating, so that means that your current is also getting modulated. So, this backgate effect is modeled by another current source, which is termed by transconductance, backgate transconductance GMB. So, this GMB will be much smaller than GM, generally we neglect it, but in case we need to consider it. Okay. Channel length we have already discussed, so we will not consider. The other short channel effects we will discuss in next class.